Very much, Dominic, and thank you for having me. My name is Rob Doomvik. I'll be your presenter this early afternoon, and we are talking about upset prevention and recovery training. A little bit about me: I'm a professional flight instructor. This is what I've been doing since about 2007. On the instruction side, I have over 7,000 hours of dual given in over 45 different airframes. I've been instructing for the last 13 years. I am a former assistant chief at a 141 program here in Boston. And I'm the co-founder of Spread Aviation, which started out as a podcast and then turned into a whole business with us providing flight instruction to customers who have their own aircraft. And we're looking to have a super decathlon for leaseback to provide services to customers out there, especially with upset prevention and recovery training. And I'm also a certified IAC regional aerobatic judge and an IAC competitor and coach. Now, there's a bit of warning, a bit of caution for this presentation. It contains a fraction of the required information for upset recovery training. Proficiency in these maneuvers should only be accomplished with a qualified instructor in a capable aircraft using proper equipment, mainly parachutes. And so what I don't want people to take away from this is that they can do this in their own aircraft, that they can do this in the Cessna 172 or 152s or Piper Cherokees or anything like that. The elements and lessons that are taught in this training can certainly be applied to those aircraft. However, for maximum safety, we try to do this in aircraft that are built to an aerobatic standard. So the Super Decathlon is my ride of choice for this. So a little bit about why we're here. My father was in the United States Marine Corps, and one of the things that I took from them was that they do more with less, and that comes from an intense training environment. And so a sign at Marine Corps Recruit Depot, San Diego says, "Let's be damn sure that no man's ghost can ever say, if only your training had done its job." And this training is meant to focus on crews just like you. And we have two folks here who were highly educated, skilled people, individuals that unfortunately we lost in an aircraft accident. So this is Captain Marvin Renslow and Rebecca Lynn Shaw, who was the first officer on the Colgan crash that went down in Buffalo many years ago and led to a lot of the changes that we've seen in our industry as far as increasing minimums, changing training environment, changing ATP requirements. And we do this in their memory. We're inspired to do this because of the lessons learned from their event. So what we talk about in this is in no means, way, shape, or form meant to put any pilots down, but it is meant to help us become better and learn from their mistakes. Nobody's perfect. I certainly am not, but we can learn from everybody. So the upset recovery training core concepts are about awareness, knowing when a situation is developing or when we're getting close to an upset, recognition, oh, now here we are, how do we fix this, and avoidance. I really, really, really would rather see it coming and take steps to avoid having an upset rather than, if all else fails, having to employ a trained response recovery. We can see here an aircraft in the inverted nose down position. You know, which button in the cockpit fixes this? And unfortunately, up until really recently, with some of the more powerful avionics systems, there wasn't a wing leveler that could really handle this attitude. And even the ones that we have, they're rate based. So it may not know that it's upside down if it's just looking at the turn coordinator. So why is upset prevention and recovery training absolutely necessary? According to the General Aviation Joint Steering Committee, the accidents that are happening from 2008 to present, when this is data as of 2015, we can see that loss of control in flight is the #1 contributing factor to fatal accidents between 2008 and 2016. Well, this is an updated chart. The one from 2001 to 2011 looks the same, and it is almost more than all the other elements combined that lead to fatal accidents. So there's controlled flight into terrain, there's power plant failures, improper fueling, unknown causes. There are a lot of different elements that are causing these fatal accidents in the general aviation world. Well, general aviation is where I spend the majority of my time, I fly little airplanes, and more than likely everybody in the training world is flying little airplanes as well. Well, that's general aviation. Commercial aviation has to be doing better, right? Well, unfortunately, the commercial fatal accidents, loss of control in flight is still the leading factor for fatal accidents around the world. So this absolutely drives home the point that it's not just us in the general aviation world, but it's also in the professional world that we're seeing these issues with loss of control in flight. Well, loss of control in flight could mean a lot of things. The causes for this are numerous. We have aerodynamic stall as number one, flight control system, spatial disorientation, icing, atmospheric disturbances, and a bunch of others. But the biggest one, aerodynamic stall, is the leading contributor. So in the flight training world, we need to ask ourselves, how are we teaching stalls? Is it a maneuver that's to be memorized and mimicked, or are we teaching the elements and warning signs with an emphasis on avoidance and recovery with those stalls? How are we preparing our students for real world awareness? When are times when we're more likely to experience a stall? What are the warning signs? What is a pitch attitude? What is the control input? What does an airplane sound like? What does it feel like? And does that tell us anything about an impending stall? So it's not like commercial operators are having accidents because they're practicing power on stalls with passengers on board. They're absolutely not. We practice stalls in the GA world, but in the commercial world, they're certainly not. They're certainly not practicing stalls in the real aircraft. However, the aerodynamic stall is the number one leading cause of loss of control in flight. So we're getting surprised as pilots due to a lack of awareness of our angle of attack. So what qualifies as an upset? Well, according to the FAA, it's pitch attitude of greater than 25 degrees nose up or 10 degrees nose down, bank angles greater than 45 degrees, or airspeed. Airspeed within the above parameters, but at airspeeds inappropriate for the conditions of flight. So if you're in cruise up at your cruise altitude trying to get to a destination, but you're doing 60 knots, or if you're in a big jet 120 knots, that's not appropriate. Your attitude may be just fine, but now you've seen your airplane is now on the edge of the flight envelope, and it's about to experience an aerodynamic stall. Now, unfortunately, from private pilot to commercial pilot, less than 0.1% of all training is on stalls, because once you're a private pilot, oh, you're good. Instrument, well, you're working on instrument approaches and BAI, and then commercial, you're working on the commercial maneuvers, and there's an emphasis there on accelerated stalls and definitely stalls in a turn. However, you're not nearly spending as much time on it as we were in private. So there is a bit of a degradation in these skills. And we can't let that happen, especially if we're going to be commercial aviators. Now, there's a little bit beyond an upset. There's something called an unusual attitude. An unusual attitude is anytime you find yourself in an attitude you don't expect to be in. And that could be, hey, I thought I was turning, I dropped my pen, I bent down to pick it up, I look up and I'm wings level. Whoa, I didn't expect to be here. Well, that's technically an unusual attitude. So part of preparing for unusual attitudes and upsets is all attitude training, all attitude envelope. We can see here in this graphic that in the blue area of the box, we're dealing with our normal flight per the upset definition, 45 degrees of bank, pitch plus 25 to negative 10 degrees. And this is just less than 5% of the flight envelope. A commercial pilot training for their rating, they may be seeing 60 degrees of bank plus or minus 30 degrees, and they're probably going to see only 11% of the envelope. So a pilot could go from student all the way to commercial, and even possibly, well, CFI you're doing spins, but all the way through commercial, and you've only ever seen 11% of the flight envelope. Well, that leaves a whole other 88.9% of the flight envelope that if you find yourself in it, you may not have the right reaction to deal with that new attitude. And your natural instinct, or the trained instinct, unfortunately, for most pilots, if they find themselves, say, upside down, is to pull. And that's not the fastest way to fix this. So with all attitude training, you definitely get to see an airplane in every single attitude and learn the quickest way back into your comfort zone, back into upright, unaccelerated, or 1G flight. And that's what we try to do in our upset recovery training. We'll show you all of these different attitudes. We'll also train you on upset causes. This is the abbreviated list from the entire ground school, but we talk about everything from environmental causes, turbulence, mountain wave, wind shear, icing, wake turbulence, aircraft system induced, runaway trim, rudder hardovers like in US Air 427, or pilot induced from fatigue, inattention, distraction, or inappropriate use of automation, or maybe even the automation failed. Well, we want to talk about all these different causes to heighten our awareness. And if we're aware of the possibilities, we can now work harder on the avoidance. I'd rather avoid than have to make a recovery. So I'd rather demonstrate, good judgment than superior skill. So here we are in straight and level flight. We've all seen this in our airplanes flying along. The horizon is out there, the clouds are up, the ground is down. And I'd like to do a little exercise here. I'm going to ask you to close your eyes. I'm going to count down from 3. And at the end of that countdown, I want you to close your eyes. And after 2 seconds, I'm going to say, okay, well, go ahead and open your eyes. And I'm going to have a new screen up. So we're going to close our eyes in 3, 2, 1, close your eyes and go ahead and open your eyes. This is an upset event plus 2 seconds. Assuming we went into, say, wake turbulence, where we experienced 180 degrees a second. Well, 2 seconds later, you're at 160 degrees of bank. Which button do you push here? What might be your natural instinct to try and fix this? Most people see a windscreen full of ground, and in my experience, their reaction is to pull. Well, we're going to talk about why that may not be the best option here. And in order to do that, we're going to kind of go back to the basics. We're going to talk about kind of Private Pilot 101. So we like to start off with the axes of flight. My favorite is the longitudinal axis. That's the x-axis, runs from nose to tail. It's the longest one. And a full rotation of 360 degrees about this axis is the motion of roll. I also talk about it as the motion from head to hip. And this way of thinking about the motion of the aircraft was developed by Rich Stoll, who's a master of emergency maneuvers and spins. But he likes to talk about it as head to hip. Rolling is a motion from head to hip on either side. And we make that by deflecting the ailerons. And that's controlled by the yoke or the side stick or the side yoke, whatever your airplane has in it. Next favorite axis is the lateral axis. It moves from side to side, wingtip to wingtip, and motion about the lateral axis is pitch. That's controlled by the elevators. And as Rich Stoll describes it, it's a motion from feet to head as a pitch up, or from head to feet as a pitch down. Well, you can't see me doing the air quotes here, but if we say rolled 180 degrees, so we were upside down, up and down no longer hold the same relationship as they did before. But from head to feet and feet to head, that still maintains its relationship. So if you are deflecting the elevators and pulling back on the yoke, that's still a motion from feet to head, but now your head is towards the ground because you're upside down. So it would be best for us to roll the airplane upright first. And the next axis, the vertical axis, here described as the perpendicular axis. Motion about it is yaw, and yaw is controlled by the rudders. So all 3 of these axes, this is Private Pilot 101, everybody remembers this. But the way that we manage an upset is going to have to do with how we manage our lift vector. So our lift equation, if we break down the different elements of lift, are the coefficient of lift times 1/2 density times velocity squared times the area of the wing. Now, if we break down the right side of this equation into the elements that we can control as the pilot, let's look at density. Can we change the temperature and pressure of the air? No, I don't think we can change that. How about the area of our wing? Can we make our wing wider or longer or thicker? Well, you might be thinking about flaps, but really the only flap type that changes the area is the Fowler flap. And we see those on swept wing airliners. And we don't really have those on our Cessnas and 172s. And it's not very often in your everyday flying that, say, ATC gives you a climb that you go, okay, I'll climb, and you put down flaps. I mean, I certainly don't do that. I'd be very interested to meet the pilot who does. Velocity squared. Velocity is another interesting one that we can use to manipulate lift. However, in this equation, it's almost a constant because we can't change it rapidly enough and in large enough amounts to generate a very large change in lift. Now, sure, as we hit turbulence or wind shear, we definitely get a change in lift there, but our power production doesn't cause us to accelerate or decelerate so quickly as to cause big changes in, say, G-force. However, coefficient of lift is certainly one that we can manipulate because it's directly related to angle of attack. So the angle of attack specifies the angle between the chord line of the wing of a fixed-wing aircraft and the vector representing the relative motion between the aircraft and the atmosphere. One of the biggest misconceptions I think that people have about relative wind is that it's always parallel with the horizon. Well, that's mainly because that's how all the graphics draw it. And even here, that's how it's drawn. We can see the angle between the relative wind and the chord line here is rather large, and that results in a very large lift vector, a large resultant force, and also a large drag vector, which is what that D is. That drag is specifically induced drag, the byproduct of lift. So at very high angles of attack, you do also have a very large amount of induced drag. If we want to increase lift, we have to increase coefficient of lift, which means increasing the angle of attack. But there's a limit to how much angle of attack we can actually increase. And that limit is called the critical angle of attack. This is the point at which it produces the maximum coefficient of lift. If the critical angle of attack is exceeded, it places the aircraft in the stalled flight regime. A fixed-wing aircraft is stalled at or above the critical angle of attack rather than at or below any particular airspeed. Now, the airspeed comment on this is one that's rather interesting because we're typically taught VS and VS1 and VSO as our stall speed and where our wing stalls, but we know that an aircraft can be stalled at any attitude and any airspeed if we exceed this critical angle of attack. And like we saw in the earlier graphic, nearly 50% of all fatal loss of control in-flight accidents are due to the aerodynamic stall. If we examine the lift curve of the subsonic asymmetrical airfoil, which is what we have on pretty much all of our general aviation aircraft, we see that there is a basically linear relationship between an increase in angle of attack on the bottom of the chart from moving from left to right and the increase in coefficient of lift moving from the bottom of the y-axis up to the top. But at some point, we can see that coefficient of lift begins to drop off. The peak point is known as the critical angle of attack, and that's for our GA airplanes, it's around 17 degrees or so AOA. It's right in this area, and that means our coefficient of lift is somewhere around 1.6 or so. I'm not going to make anybody do any math, but we need to understand that we are controlling, as the pilots, the angle of attack by the positioning of our elevator and the positioning of our yoke or stick or side yoke, whatever our pitch controller is in the aircraft, that's directly controlling our angle of attack. So if anybody is looking at upgrading their airplane with an angle of attack indicator from Bendix King, let me save you a couple $1,000s. You've already got an angle of attack indicator in your airplane, and that's the stick. You just got to learn how to use it. That's part of where this training comes in. One of the other big misconceptions I see is people have a little bit of a misunderstanding between pitch attitude and angle of attack. And even this graphic is still showing flight path angle still air in relationship to, or at least showing the horizon, showing how we can have two different angles between flight path and actual pitch attitude. But remember that the relative wind is parallel and opposite the flight path. So we can clearly see in this that our relative wind is flowing this way and our angle of attack is up in here, difference between the velocity vector and the actual pitch attitude of the aircraft. All right, drag. We talked about drag a little bit before. A drag is a mechanical force generated by the interaction of a solid body with a fluid, and liquids and gases count as fluids. Drag is a force and a vector quantity having both a magnitude and a direction. In this case, it acts in a direction opposite to the aircraft's motion. And the drag equation is very, 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 very similar to the lift equation. As you get thicker air, there's more parasite drag. As you pull more coefficient of lift or more angle of attack, you get more induced drag. And so all of the drags are actually accounted for in this equation between the area of the wing, the velocity, the density, and the coefficients. So we can actually use drag to manage our velocity in an upset. Say we were nose down, we can use the max G of our airplane in a recovery to help generate max induced drag to keep our airspeed from exceeding VNE. But you do still have to be careful, because at high speeds, you can generate more G than the aircraft is certified for. This brings us to stall speed and how we use angle of attack to manipulate our stall speed. Now, the weight of the aircraft and the felt weight of the aircraft are what the wing is counteracting with its lift production. As an aerobatic competitor, I have been at the top of loops where I was showing 0 airspeed, but I had no stall warning indications. The wing wasn't buffeting, it was still flying, and because my stick was basically centered, I wasn't generating any angle of attack. There was no loading asked of the airplane. So I was at a very, very low speed, but because the wing wasn't being asked to produce lift or support the airplane, I wasn't stalled. Now, this also goes the other way. If anybody is familiar with World War II aircraft, there was a very awesome airplane called the Curtiss SB-2C Helldiver. And the reason it has that name is because it had a very bad reputation in the development of the aircraft and in training with the aircraft, because the flight profile for its mission was a dive bomber, and it would attack aircraft in a very steep dive. Well, the pilots would be doing 500 miles an hour, and they'd pull back really hard on the stick after they dropped their bombs, and the aircraft would change pitch attitude very rapidly, but it couldn't change its flight path away from that steep descent as quickly as it changed attitude. And so it exceeded its critical angle of attack at very, very high speeds. Now, fortunately, a handful of pilots were able to recognize the aerodynamic stall and recover from it and managed to get the aircraft back flying again and climb out. And when they went to talk to the engineers about what was going on, the engineers would ask, well, what was your speed? We're doing 500 miles an hour. Well, you can't stall at 500. Well, that's not true, because I was doing it. And that just shows in World War II, even some of the training didn't really understand where the stall was coming from, and that it was related more to angle of attack than it was to stall. So what we see and we learn in our aircraft as our stall speeds, those are based on the 1G max gross weight full forward CG condition. As your weight goes down, that stall speed actually goes down. And we'll actually show a graphic a little bit later that demonstrates how we can manipulate our stall speed with angle of attack and unloading the wing. But just as a refresher on stall and some of the stall characteristics to be aware of to heighten our awareness, some stall characteristics may be buffeting, lack of pitch and or roll control, an inability to arrest descent rate, continuous stick shaker if you have one of those installed on your aircraft, oral and visual warnings. So you might have the stall warning horn going off in your ear, or you could have the little light on the dash and the pipers that says stall on it coming on. And for our Part 25 transport category aircraft, uncontrollable nose down pitching, control column at aft stop, or a state of deterrent vibration. And for me, the biggest one there, the most important one there, and I've talked about this a little bit earlier, is this control column at aft stop, meaning, hey, if you're pulling all the way back, whether you think you are or not, you're stalled. And we see evidence of this on Air France 447, where they went from 36,000 feet down to around 10,000 feet with the control column being held on the all the way back position. An airplane that was capable of flying, but they were pinning it in the stall. And if we examine Colgan 3407, if you watch the animation of the flight data recorder, the control column, the yoke is pulled all the way back for the duration. And that airplane really, really wanted to fly, and all they had to do was really relax that back pressure, and that wing would have started flying again. And so that control column at aft stop, we need to be thinking to ourselves when we're flying our airplanes, if I'm pulling back and getting further and further back, but I'm in a position, a situation where I don't want to be stalled, like, I don't know, base to final, we need to relax that back pressure, unload the aircraft, roll upright, add the power, go around, come back and try it again, do something different. But following that trend of continuing to pull back on that control column or that yoke or that stick or that side stick or whatever your pitch controller is only going to lead to the same place that every other power on, power off, stall, or really any landing you ever did in your training was. And if you think about your training, if you think about all those power on stalls and power off stalls, where was the yoke? Where was the stick? Where was the side stick? Where was your pitch controller when the stall break happened? I guarantee it was further back than it was forward, if not all the way back at the stops. Airshow pilot and Patty Wagstaff School instructor Spencer Suderman has recently stated, airplanes stall when pilots command them to. So it's about our input. It's about what we're doing as the pilot. And so we're the ones that are responsible for stalling the aircraft, but we're also the ones responsible for recovering. Now, in this training, we will talk a little bit about spins, but if you're following the tenets of upset recovery training, you won't put yourself in a position to even have a spin, because a spin requires two elements, stall plus yaw. If you don't stall the aircraft, you can't have a spin. But we do advocate the pair recovery, power idle, ailerons neutral, rudder opposite, and elevator neutral. This is also known as the NASA standard spin recovery. Once you have the aircraft, once you have the rotation stopped and the wing is now flying again, you can execute your recovery, roll wings level to the nearest horizon, and recover from the dive. We won't necessarily focus on spins during the training. However, we do talk a little bit about it. So again, here we are at our upset event plus 2 seconds. 9 out of 10 without dedicated upset prevention and recovery training will pull in this position. And that comes down to a little bit of startle factor. When we're suddenly exposed to a reality we did not expect, our reaction to it is either going to be a trained reaction or it's going to be a panic reaction. Now, the British SAS is a special forces team, and they did some studies. I think this was in the 80s or 90s. I'm not quite sure exactly when it was, but they did some studies where they took untrained individuals and exposed them to a threat. And it took these untrained individuals 10 seconds to respond to the threat. And when they took trained individuals and exposed them to the same threat, they responded within 3 seconds with an effective counter to the threat. So it's not just about reacting quickly, it's about reacting quickly and appropriately. And our first move that we really want to make in the upset recovery world is to unload. Upon recognition that the aircraft is about to exceed or has exceeded upset parameters, we want to unload the aircraft. We want to take that control column and we want to push it maybe slightly forward from neutral. And our target here is a G load of approximately a positive quarter to a positive half G. This does some really positive things for our aircraft. Number one, it maintains the normal flight regime. Still positive G. You're still flowing fuel. You're still circulating oil throughout your engine. You're not necessarily spilling the coffee out of the coffee cups. It expands the normal flight envelope, meaning the aircraft now is capable of flying actually slower than if it was at 1G. Like I talk about in the loop example where I'm at the top of the loop and I'm showing no airspeed, but I'm still flying. My wing is still installed because I'm unloaded less than 1 positive G. It stabilizes the airspeed because we're no longer fighting as much induced drag. So whatever power we have acting on the aircraft actually doesn't have to fight as much drag anymore. And that's kind of a good thing. Unloading also optimizes the aircraft roll capability by allowing the wing to not concentrate on having to support the aircraft and roll the aircraft. When we unload it, now the wing has to roll an aircraft that effectively weighs half as much or a quarter as much. You take a 2,000-pound airplane, now suddenly weighs 1,000 pounds. Yeah, that's going to be a whole lot easier to roll. Or now weighs 500 pounds, or it feels like it weighs 500 pounds. Yeah, that's going to drastically increase the roll rate of the aircraft. Unloading also minimizes something called asymmetrical rolling G, which in my opinion, well, asymmetrical rolling G is one of those things that in 1996, the Air Force grounded the entire fleet of F-16s because there were cracks in the wings. And what they discovered was there was asymmetrical rolling G going on. So we got to repair all these wings because pilots were rolling and pulling at the same time. In 2000, and I think it was 10, the Air Force did the same thing with the fleet of F-15s. Asymmetrical rolling G, they're cracking the wings. And in 1951, out of Akron-Canton Airport in Ohio, there was a P-51 base where they were having wings break off their airplanes. And it was, hey, what were you guys doing when this broke? Oh, we were dogfighting and we were rolling and pulling. Oh, you broke your wings. And what that does is it reduces the G load limit by a third. All right, more on that later. But as far as the unload is concerned, we're targeting that positive half to positive quarter G, which is a little bit tricky. You want to push forward, but you don't want to float the dog. That poor little puppy right there. So they actually got probably a little, they were at 0G and probably a little bit negative that got him to float up there. But poor little guy, he'll be all right. Don't go doing that in your airplanes. So load limit versus level flight. So in our aerobatic airplanes, 6 Gs is kind of like the lowest you would see on an aerobatic airplane. That's a super decathlon. You are able to, at max G load, you're able to maintain level flight up to 80.5 degrees of bank. So it takes just that much to maintain altitude at 80 degrees of bank. So if you do find yourself in an upset, you may not have enough G load available in the aircraft, depending on your bank angle, to maintain level of flight. For our Cessna 152s with a utility category, or even if you got a lightly loaded 172, you're able to maintain level flight at about 77 degrees and max G, max pull. Normal category 3.8 G, 75 degrees, and in biz jets and airliners, 2.5 G limit, transport category aircraft at 66.5 degrees, you're able to maintain level flight. Well, that 2.5 Gs would be a whole lot better suited to get you away from the ground if you were at 0 degrees of bank. So if you actually roll the airplane upright first and then go for your pull, you'll be in a whole lot better shape. So there's limits to what the aircraft is capable of doing. When we talk about unload and expanding the aircraft's operating envelope, what we mean here on our 1G stall speed, we can see it's for this fictitious aircraft, 1G stall speed is about 64, 65 miles an hour right down here. We can see this on the markings down here. If we unload to a half G, right in this area right here, we now have dropped our stall speed significantly lower than the 1G stall speed. We're losing almost a third. And now if we head down to our quarter G stall, now we're down around 27 knots on our previous 62 knots. So the wing is still flying. It's still supporting the aircraft at this quarter G, and it's not stressed. It's not loaded up. So if we do find ourselves nose high and running out of energy, running out of airspeed, we got to get this unload going before the wing stalls and help prevent that wing from stalling. But you don't want to go too far, because even at negative 1G, we can see this dark blue line here. At negative 1G, the wing stalls at 80. Now, most general aviation airplanes barely have enough elevator authority to get you into the negative stall. But this just goes to prove that each airfoil has two critical angles of attack, one positive and one negative. For inverted flight or negative G flight, you can actually stall it by pushing too hard. So don't float the dog. Don't stall yourself in the negative. So once again, you get here knowing how bad pulling is for us. Do you really want to pull? What if you're 60 degrees nose up? You know, they say pull back to go up, pull all the way back to go down. And if you're nose up, pulling back more isn't going to help you at all. The unload helps to stabilize the airspeed by increasing our rate of acceleration. And the areas that we're operating around sea level, between sea level and 10,000 feet, we're generally getting somewhere between a 5 to 20% increase in acceleration. This is something that's important for racers. So when Red Bull was a thing, those guys needed to unload on the downlines. But if you find yourself in a nose high attitude and you're running out of airspeed real fast, helping to unload that aircraft is going to help that engine producing max thrust to keep that airspeed from going any lower, so we don't have to flirt with the edges of the envelope. Optimizing roll capability by reducing and eliminating adverse yaw. Adverse yaw is the yawing moment opposite the direction of the initiated roll due to increased induced drag created by the depressed aileron on the rising wing. You've probably had flight instructors be like, hey, you got to stay coordinated. I teach whichever direction you're deflecting those ailerons, you need to have a little bit of rudder in that direction as well. And that's because you have a differential in lift between the two wings that generates that roll. Well, we already know that lift makes induced drag. So you have a differential in induced drag as well. By unloading, you eliminate or minimize the differential in induced drag between the two wings, and you actually need even less rudder if you are unloaded during your roll. This is something we use in the aerobatic world quite a bit. At zero lift, the upper and lower wing surface lifts are equal, and by unloading, we're helping to get it there. Yaw due to roll is primarily a function of wing coefficient of lift and is greatest at high coefficients of lift. So if you're rolling and pulling, you're actually doing the opposite of this. You're increasing the amount of induced drag on the wing, and that is causing a bit of a twisting force on the wing. That will cause the rear spars to fail, and we've seen some structural failures even recently in the Piper aircraft, the Aero down at Daytona Beach. That was a rather new aircraft, but I suspect during its life it had been exposed to some asymmetrical rolling G, mainly because we didn't know any better as pilots. We didn't know to teach it. So unfortunately, we're trying to save lives, or fortunately, we're trying to save lives just with a little bit of knowledge. Zero lift between a cambered airfoil, asymmetrical or asymmetrical airfoil. We can just see that there's two different centers of pressure. However, the magnitude of them is equal, and that wing is actually rather happy. And the asymmetrical airfoil, it takes a negative angle of attack in order to get to zero net lift. On an asymmetrical airfoil, zero angle of attack means zero coefficient of lift. But there's a penalty on the positive lift side. Symmetrical airfoils are great for aerobatics, not so much for GA or airlines or really even fighters. They have symmetrical or asymmetrical airfoils as well. And all of this is about managing our lift vector. We saw this graphic a little bit earlier, but what we're trying to teach with upset recovery training is that this relative wind that we see in line with the horizontal could be coming from wherever our attitude is through all 360 degrees of the flight attitude. The way that we manage our lift vector is how we get our aircraft going where we want it to go. So flight path versus lift vector is how we make the aircraft turn. It's how we climb. It's how we descend. It's how we maneuver, period. And so the way we manage that lift vector, say knife edge and beyond, is very important. We don't want the lift vector contributing to gravity if the aircraft is upside down, or at least we want to minimize the lift vector's contribution to gravity. The unload, going for that half to a quarter positive G, shrinks that lift vector way, way down in order to minimize that contribution to gravity, and also allow us to roll our airplane as quickly as it can possibly roll back to upright flight, where our lift vector can now do what the textbooks say it's supposed to do, and that's fight gravity. So we need to get it there by rolling the airplane quickly. Asymmetrical rolling G, we can see that this aircraft is rolling to the pilot's right, our left as we're looking at it, but rolling to the right means that you have an increase in lift on the left wing and a lower amount of lift on the right wing. If we can reduce that, if we can reduce the differential there, we're in better shape. But this immediately reduces, an asymmetrical rolling G reduces the G limit of the aircraft by a third. You essentially drop a category. Aerobatic becomes utility, utility becomes normal, and normal comes down to just about 2.5 G. There's a little bit of difference there, but basically you drop way down on these G limits, and so then it becomes even easier during an asymmetrical rolling G event to overstress your aircraft. So maneuvering speed, we talk about maneuvering speed quite a bit. Just a refresher, this is the highest speed at which full and abrupt control inputs may be employed without exceeding the structural limits of the aircraft. And this definition, however, assumes that the full and abrupt control inputs occur on one axis only. So if you're making a full-scale deflection of your ailerons, okay, that's what you get. And it also means that it's only in one direction. So if you're rolling hard to the left, don't slam it back to the right, slam it back to the left. The same with the rudder. And the same with the elevator. Don't go full back, full forward, full back. You're asking to overstress your aircraft. So VA is one direction, one control surface, one time. If you need to reverse, you need to come back to neutral for a brief enough pause to let the forces neutralize, and then you can reverse and initiate an opposite direction if necessary. So I'm hammering the unload here, because it's very, very important to us. It's the first step in an upset recovery. It keeps the aircraft in the unstalled regime. It expands the normal flight envelope. It stabilizes the airspeed. It maximizes roll rate and minimizes destructive asymmetrical rolling G on the aircraft. Our upset recovery profile that we teach is attitude. This is the first time that you may be aware that something bad is happening. Disconnect autopilot and autothrottle, stow the speed brakes if in use, and unload. Target that half to a quarter G. Recognize the attitude, whether it was nose up or nose down. You need to power up or power down. Roll the aircraft to either the nearest horizon or the 45 to 60 window if you were nose up. Recover the aircraft. So we teach, go for a VY climb. I don't know how much altitude you've lost in your upset in the event. We don't know. I don't know where the terrain is. I don't know where the obstacles are. So let's go for that VY climb once we have that wing flying again. And then we can assess airspeed, altitude, aircraft controllability, air crew, and ATC. Hey, is everybody all right in the back? ATC, hey, we just flew through something. We don't know what it was, but let everybody behind us know something might be there. Our upset recovery training profiles. We do nose high over bank. So we'll take you beyond 60, 90, 120 degrees. We'll put you over on your back and make you fix that. Then we do our nose low and our nose low over bank. And we do some freestyle recoveries where I won't necessarily put you anywhere specific, but I will put the airplane in an attitude you may or may not have ever seen before. And I'll say, okay, recover. And it will be up to us to fix it. A note about the rudder here. The rudder will create a marginal rolling response. The rudder's purpose, however, is to create or cancel yaw, and yaw is not a roll. This recovery procedure does not advocate the step on the sky philosophy. Large rudder inputs will uncoordinate the aircraft and potentially overstress the tail assembly. We don't want to uncoordinate the airplane because if we do accidentally stall it, now we have stall plus yaw, and that's the ingredients for a spin. Never apply a full deflection of the rudder or any other control surface, followed immediately by a full deflection in the opposite direction. If yaw is detected, make a single rudder input to stop the yaw, then neutralize the rudder. By going through the steps to unload the aircraft, we're getting rid of the majority of what would be uncoordinating the aircraft in the first place. So at that point, the rudder is no longer really needed. So I want to thank everybody for joining us. I want to see if there are any questions that anybody has while we're here. Dominic, come on back in. Thank you for letting me have the stage there. And a lot of this material was developed by a Bad Attitude Aviator Training Company, which I was a part of back in Ohio, back in 2007 when they first started, before I moved out to Boston. And so a lot of these concepts came out even before we were having this big push, this big emphasis on upset recovery training.
And thank you, Rob. That was incredible. I hope everyone took away as much from that as I did. And hopefully a few more people are getting more excited about upset recovery and prevention. If anyone does have any questions, please feel free to unmute yourself and ask Rob, or you are also free to type them in the chat box on the side below.
Well, that's good. Everybody was quiet and attentive while the presentation was going on. That's good.
Yeah.
This is what I looked like while I was over here talking to the microphone.
Does anybody have questions for Rob? I have a couple people coming back in.
Oh, did we lose connection? That's no bueno. All right, well, while people are getting their questions together, just want to take this time, thank you everybody for joining us. Later on in the afternoon, we're going to have a couple other presenters. They won't be, I don't think they'll be in this channel, will they, Dominic?
No, there will be separate links that people can have. It was all included in the SPANS event and the emails that were sent out. So
yep.
You can the event through different links.
Yeah, so we've got Stephen Brown from 3 to 4 from the Boston FSDO, and he'll be doing Boston area recent accidents, incidents, and trends. This is a fantastic presentation that they typically did every year at the safety stand down at the Doubletree here in Boston, and it was great to go over some of these different things. And a lot of the accidents that were talked about there had elements that were upset prevention recovery training related. Aerodynamic stall was definitely one that led to some of these issues, and even base to final overshoots and stall spins at low altitude, things that, hey, if you're aware, you can avoid this stuff instead of having to recover from it. Let's see, Chris Parita is going to be after that, talking about CBD oil and other medical legal trends. And from 5 to 6, Mark Medvets, retired American Airlines captain, will be presenting on airmanship. So check those out and get all your wings credit for the day. Knock it all out. I don't know.
A good way to spend a Friday. I think someone did just unmute, by the way. Did someone have a question for Rob?
Yeah, actually, this is Stephen K. Brown. Hi, Rob. How you doing? I was going to make a comment. Terrific presentation. Thank you. But terrific opportunity, and you can see this expand into other parts of aviation, as Rob probably knows. Fly gliders fair amount, and just this past weekend was doing ground launching, winch and auto tow launching, which when the acceleration stops because of the winch breaking, a rope break or something like that, the most important thing right there is to unload and reduce the angle of attack. And it's a type of event that occurs very close to the ground. So all the things that you're talking about are essential training elements in that type of environment. So
absolutely
very good. Yeah. Thank you.
Yeah, and the management of the angle of attack, that was one of the things I this presentation is set up for fixed wing aircraft. So it's not just powered aircraft, it's everything that's fixed wing. Don't really talk about helicopters here because that's not my area of expertise at all. But these are techniques that work in every fixed wing aircraft at any altitude up and into the flight levels. And we have trained airline pilots as well, and very light jet operators in these concepts. So this is stuff that we've been doing for about 13 years, and me here in the Boston area since 2013 when I brought this training to Executive Flyers Aviation, which is no longer here.
And something else too, Rob, I wanted to make sure you had ample time to share that as well. While people are preparing questions, how can people get in touch with you if they're looking to do upset recovery training?
Yeah, so right now, I would love to recommend me. We don't have the aircraft yet on leaseback. We're working on it. Hopefully by the end of August, we'll have a super decathlon that will be able to offer this training in the New England area. However, some of the best schools around the country are Bad Attitude Aviator Training Company out in Ohio, Patty Wagstaff School down in St. Augustine, Florida, Sean D. Tucker School, and APS training. APS, I think, is in Arizona, Nevada, New Mexico. They're around those areas. They may even have a couple other locations as well. And they mainly do it in the extra. So it doesn't really matter the airframe so much. It's about the content of the training. And unfortunately, after 2009, a lot of these schools popped up. And when we were doing our research as to, okay, well, what's your profile look like? We were not happy with where their emphasis was, and it wasn't on the airmanship anymore. So I don't want to tear those other schools down, but I know that the schools that I've mentioned already do have a very quality product that is something that is going to save you in the event of in the unlikely event, hopefully, that you ever do experience an upset and have to deal with it. I have had a handful of real-world upsets in the aircraft, not only in the aerobatic world, but also in the instrument flying world, and even some emergency flight situations where it was most important to keep that wing flying. And as Bob Hoover says, fly the airplane as far into the crash as possible. And mainly that means keep that wing flying by managing that angle of attack.
And I had a first here, which was the email question. So someone sent me a direct email question for you, Rob.
Cool.
So someone flying jets was wondering, if I had to choose a platform, you mentioned APS. They fly, I think, some sort of military type trainer and extra 300s. But if someone's a jet pilot, do you think the transition training from the extra and applying it to a jet aircraft would be suitable, or should they be looking for jet-based UPRT?
No, the jet-based UPRT stuff in our research wasn't necessary. And I'm not naming any names here, but for some of the companies that we looked at, you were basically paying for them to go fly their jet around and you do loops and rolls in the sky. Whereas if you get into the extra or even the super decathlon, the performance of those aircraft mimics the lack of control or the lack of dampening that you experience in your jet up at high altitudes. So without thick air, your airplane, your jet, is going to perform in a way that you've never seen it before. It's going to roll faster than you've ever seen it before. So to get into the extra, which has a slightly faster roll rate than what you may experience, you're now having to deal with something that is an even bigger threat or an even bigger challenge. And so any lesser challenge, you're better capable of dealing with. And that's one of the ways that I like the extras and I like the super decathlons, is that they challenge you in a way that's preparing you better to deal with anything that may happen up in your jet. And I think the biggest example of that recently is the Challenger over in Spain, I think it was, that went into the wake of the A380, and they rolled and bent the heck out of that jet, actually totaled it. It was a miracle that it stayed together and got them on the ground. So I mean, that was a big statement to the strength of a Challenger. However, if their first move had been to unload the jet and fight the roll, the airplane would have been at a half G. It wouldn't have spiked over the G limits. They may have had a better opportunity to fight that roll rate as well, because in wake turbulence, generally you're going to see around 80 degrees a second. You can certainly unload and roll one of those biz jets around 80 degrees a second. At least hold yourself in the attitude, and you got altitude to trade. So hold the unload until you actually exit that phenomenon and you get roll authority back. Get yourself back up to wings level and go back for that VY climb.
Awesome. We had another question pop up in the chat box from Jordan. It says, in terms of VA, so in terms of maneuvering speed, since the positive and negative load limits are usually different, say positive 3.8 versus negative 1.52, do you have to be careful when pushing forward on the control column as opposed to pulling back on the control column, even if you are below maneuvering speed?
I say that the forward is going to be your safer direction, because again, remember, you're targeting just a little bit light in the seat feeling. You don't want stuff to be floating around the cockpit. So that's a positive quarter, positive half G, which is still a ways away from your negative 1.78 or 1.52 limit on the negative side. Also, the design of the aircraft, the elevators aren't generally so effective that you're going to get to that low end G before you hit, say, a negative stall. The elevators just aren't built that strong in GA airplanes. Aerobatic airplanes, yes, they are. We need that. But your target goal, remember, is nowhere near that negative G limit. It's just at that negative half, or not that positive half and positive quarter G, which is just a little bit light in the seat. Part of the training exercise that we do on flight number 1, flight number 2, flight number 3, flight number 4, while we're flying out, is we practice this half G unload, so you know what it feels like to hit that negative or that positive half G, and you don't go beyond that. It's a very good question, actually. It's a very good question.
Yeah, thank you, Rob. Thank you, Jordan. Anybody have any additional questions for Rob?